So today we'll start with a new unit, that is electrogravimetry and coulometry. So we are gradually completing one electroanalytical techniques. So the electroanalytical technique that today we will be dealing with electrogravimetry and coulometry, and today we will discuss it in details. So the contents of this chapter is what is the definition of electrogravimetry, polarization, the different types of gravimetric electrogravimetric methods, then introduction to coulometry, the different types of coulometric methods, and they are summarized the overall chapter. So first we'll start with the introduction to electrogravimetry. So here is, what do you mean by electrogravimetry? So this word, it consists of the electrogravimetry. It means it is a combination of two words. One is the electrochemistry and second is the gravimetric. So whenever we talk of gravimetry, it means that we are dealing with the weight of the substance. So here electrogravimetric analysis, it is similar to that of conventional gravimetric analysis. Now, gravimetric analysis means that we determine the weight of the substance before and after the reaction. So, and electrogravimetric means the measuring of the weight of our sample before and after the process of the electrolysis. So, the material is deposited on an electrode by application of an potential instead of a chemical precipitation. So, hence, because we are using the process of electrolysis that is employed here, then the whole process is termed as electrogravimetry. Now, before understanding the principle, we should understand we should learn some of the important terms that are used in electrogravimetry. So first, from potentiometric studies, we know that what is a cell. So we know that a cell, it consists of two electrodes that is immersed in an electrolyte. There are two types of cells that we have talked of. One is a galvanic cell and another is an electrolytic cell. So a galvanic cell or a voltaic cell, it is a device that is which is contains which converts chemical energy into electrical energy. The galvanic cell usually consists of two electrolytic solutions in which two electrodes of different materials, they are dipped in it. And Daniel cell, we know it is one of the most common example of a galvanic cell. So when we supply energy from an external source, the cell through which it flows, that is the overall cell where the electrochemical process it occurs, that process, that whole cell is known as electrolytic cell. So irrespective whether the cell is galvanic in nature or electrolytic in nature, we call the electrode where oxidation takes place as the anode and where reduction takes place as the cathode. So this is uh, a general concept that we have to remember through the process of electrochemistry, that is the electrode where oxidation occurs, that is always the anode, and the electrode where reduction takes place, that is always the cathode. So this is a very conceptual thing in electrochemistry. In potentiometry, we have already learned that cathode is a positive sign and an anode is given a negative sign in a galvanic cell. But when in an electrolytic cell, these electrodes, they acquire charges opposite to that is in potentiometry. So the capacity to do electrical work by a cell, it is called as the cell potential, and it is measured in terms of volt. Now an example here it has been given here, that is, let us consider a cell of the type where copper is deposited at the cathode and oxygen is evolved at the anode. So the overall cell reaction, it can be written as copper 2 plus 2H plus forming half O2, and then is the platinum electrode. So the cathodic reaction, the reaction that occurs at the cathode, is given as Cu plus 2 plus, it takes up two electrons forming Cu0. At the anode, this mercury HgO, it breaks to form 2H plus, sorry, this is H2O, HgO forms 2H plus half O2 plus copper oxide, and the overall reaction is given by this. So the potential of the electrochemical cell, that is the E cell, it is defined as the difference between the electrode potential between the cathode and the electrode potential of the anode. That is, in simple terms, that we already know, we can write it as E cell is equal to E cathode minus E anode. This is always E of cathode, that is the half cell potential, that is the potential of the cathode, and E anode, it represents the potential of the anode. So here in figure 5.1, an electrolytic cell, it has been shown. So a voltage in this circuit, a voltage E is so here, in this figure 5.1, a simple electrolytic cell is given. Now to this cell, we apply a voltage. Let the voltage be given as E applied in such a way that a current flows through the cell. After we apply this voltage, current start flowing inside the cell. Now what happens is, when this applied voltage is greater than the cell potential, then there will be flow of current in the circuit. So when there is a current, then the potential of the cell, it is less than the thermodynamic potential, because one or more of the following phenomena occur. And what are those? That is due to IR drop, concentration polarization, and kinetic polarization. Now coming to these three terms, so what are the three terms that occur that during the process of current flow within the cell? First that occurs is called as IR drop. We call it as ohmic potential. Now we know from Ohm's law that V is equal to IR, or E is equal to IR. So here the term IR drop is called as ohmic potential. The electrochemical cells, like normal metallic conductors, they resist the flow of charge. So in both the types of conduction, the Ohm's law, it describes the effect of resistance. We know that resistance is described by Ohm's law. The product of the resistance R of a cell, that we should take in ohms, and the current I in amperes, we call it as the ohmic potential or the IR drop. So I represents the current and R represents the resistance. So overall, the product of this I and R is called it's the IR drop, or we call it as the ohmic potential. So we know that when the applied potential, that is E applied, is equal to the cell potential, then there will be no flow of current within the cell. When we gradually increase the applied potential and it exceeds the E cell, then a small current, it appears in the circuit. So this current, that through the cell it encounters a resistance of R, which results in the formation of this minus IR. That is what we call it as. In other words, the applied potential, it must be greater than the ohmic potential or than the IR volts, so as to current should flow within the cell. So this E applied, mathematically we can write it as E applied is equal to cell potential minus IR. So here the E applied, if we elaborate this, we can write it as E applied is equal to E cathode minus E anode by minus of IR. So the above equation, if we rearrange this, then we get the equation that is shown here in figure 5.3, that is I is equal to E cell minus E applied by R. So that is the current that flows within the circuit is given by the cell potential minus the applied potential divided by R. So this is how we define the current that flows within the circuit. So for small currents and brief periods of time, the E cathode and E anode, they remain relatively constant during the electrolysis. So the cell behavior can be represented by the reaction, that is I is equal to minus of E applied by R plus K, where this K is a constant that of the overall electrolytic cell. So now in figure 5.2, a plot of current versus potential, it has been shown. Here in x-axis we could see the E, and in y-axis we could see the current I. So as shown in figure 5.2, a plot of current as a function of applied potential in an electrolytic cell, it should be a straight line with a slope that should be equal to that of the negative reciprocal of resistance. That is, theoretically speaking, what should be the nature of the I versus E curve? So here it should, the I should be taken in y-axis, the potential it is taken in the x-axis, and if you plot this, then it is a straight line, and the slope of this plot is minus 1 by r. But what happens is, in actuality, there we observe certain deviations. So even normally the deviations here, it has been shown here for an electrolytic cell and for an galvanic cell, there is certain minor deviations from the theoretical plot. So here in figure 5.3a, we see that there is a very slight deviation. This is the actual plot and that is a slight deviation. But when we consider a galvanic cell, then the current it deviates significantly from the actual plot. So here this is due to the, in there is a difference between theoretical part and practical part. So cells that exhibit non-linear relationships, they are said to be polarized, and the degree of the polarization is given by over voltage or over potential. Now this is an important concept, the concept of over voltage or over potential. So polarization requires the application of a potential greater than the theoretical value to give a current of the expected magnitude. Thus, an over potential of minus 0.04 volt is required to obtain a current of 0.06 ampere. So, as illustrated here in figure 5.3a, we see this difference, the difference between the actual estimated value and that we are observing, it gives rise to the over voltage. So in a galvanic cell, the output cell potential decreases by 0.03 volt, that is the over voltage is 0.03 volt. Here it has been shown. So since the deviation is this, the minus 0.03 volt, we say that the over voltage is 0.03 volt. Now we should note that in both these cases, if we look into the over voltage value here in figure 5.3a, it is minus 0.04 volt, and in figure 5.3b, it is minus 0.03 volt. So in both the cases, we see that the over voltage is negative in nature, although we write it as positive, but over voltage is always negative. So hence, for an electrolytic cell which is affected by over voltage, the overall equation it becomes the applied E, that is the applied voltage, is equal to cell potential minus the ohmic drop, that is I into R, minus the over voltage. So in simple terms, we can say that the over voltage is the potential difference between the theoretical cell potential, which is determined from the above equation, and the actual cell potential at a given level of current. So on the other hand, polarization is the departure of the electrode potential from its theoretical value on passage of current. So here the further explanation has been done in the next part. Then that the next part is the polarization. So let us consider the situation that we have first shown for over voltage in figure 5.3a. Now what happens here is, if we increase the applied potential, then the current becomes independent of the applied voltage. So this gives rise to a limiting current as shown here in figure 5.4. So here in figure 5.4, it is the current potential curve for electrolyte illustrating ohmic region and limiting current. So this is the as we keep on increasing the voltage, it increases linearly. Then at a point it undergoes limitation. So at the point where the limitation or the saturation starts, that point is called as the onset of polarization. So polarization can be conveniently, it has been divided into two subcategories. So one is concentration polarization and the other is kinetic polarization, or what we call it as the chemical polarization. So this polarization, it is an electrode phenomena and it affects both the types of electrodes that are present in the cell. So here first we will start with concentration polarization. When ions are discharged and deposited on an electrode as a result of passage of current, the area in the immediate vicinity of the electrode is depleted of ions and the layer offers resistance to the passage of current. So this type of resistance that occurs due to the changes in concentration of the electrolyte around the electrode is known as concentration polarization. So this polarization, it occurs when the ions do not arrive at the cathode, or the product species do not leave the anode fast enough to maintain the desired current level. So we have already seen that reactants are transported to an electrode surface by three mechanisms. What are those three mechanisms? One is diffusion, migration, and convection. So this concentration polarization, it arises when the effects of diffusion, migration, and convection, they are insufficient to transport the ions at a rate that produce a current of desired magnitude. So if the depleted area in the vicinity of the electrodes is not supplied with the counterpart ions, then the bulk of the solution, it is increased by diffusion or convection. So then the cathode will assume a more and more negative potential, and the applied potential is increased. So as a result, a back EMF is set up, and this, so to overcome the polarization, a back EMF is set up, and hence the concentration polarization, it requires applied potentials that are larger than the theoretical value to maintain the overall balance of the current in the electrolytic cell. So now coming to chemical polarization or kinetic polarization. So this polarization may occur due to changes in chemical nature of the electrode deposition of another metal, or due to the coating of the electrode with a layer of gas such as hydrogen or oxygen. Kinetic polarization may be also caused by the formation of films on the electrode. For example, an aluminum anode, it is liable to be passivated by a coat of alumina that is present on it. Kinetic polarization, it is most pronounced in electrode process that yield gaseous products. Now this is known as gas over potential. Gas over potential is a very common term in kinetic polarization. So over potential, it depends on several factors such as electrode material, current density, temperature, pH, etc. The over potential for many metals, they differ accordingly. Voltage at a given current density, it decreases if the electrode surface is roughened. This is due to an increase in effective surface area and the consequent decrease in actual current density. So in increase in current density, invariably it increases the over potential to a limiting value. As the temperature increases, the over voltage decreases. So hydrogen over voltage, it is the greatest in metals such as cadmium, lead, tin, and lead, tin, zinc, and mercury. So one of the essential requirements of electrode deposition is that the deposit must be compact, fine, and adherent to the electrode. Simultaneous evolution of gas results in a very spongy deposits. So complex ions, they yield smooth deposits. For example, silver, when deposited from silver cyanide complex, it yields a very satisfactory result. Then what is the importance of this over voltage? The existence of over voltage, it explains various types of phenomena. So for example, in a lead accumulator, during charging, the metal is deposited on the cathode instead of hydrogen being evolved due to the high over voltage of lead. It is possible to deposit electrolytically the metals which have a more negative potential than hydrogen, such as zinc, cadmium, tin, etc., from an acid solution because of the high over voltage of hydrogen on such metals. Overvoltage plays an important role in the industrial production of chlorine and sodium hydroxide by the electrolysis of brine sodium chloride solution. And when the electrodes of high over voltage, they are used in electrolytic reduction, it means to increase the reducing power. So electrodes with high over voltage like lead, instead of platinum, they are used in organic electrolytic reductions to get the desired products. Then coming to types of electrogravimetric methods. So electrolytic precipitation or electrodeposition, it has been used widely to know the amount of metal that is deposited during the process of this electrogravimetry. So in most applications, we know that the metal is deposited on the platinum cathode and increase in mass is determined. So there are two types of electrogravimetric methods. So one is constant current electrolysis and the other is constant potential electrolysis. So first is the constant current electrolysis. Now, as the name implies, this process occurs when there is constant current flow through the circuit. So herein the electrode deposition is carried out by keeping the current constant. So the periodic increases in the applied potential are required as the electrolysis proceeds. Now here as shown in figure 5.5, this is the apparatus for constant current electrolysis. The apparatus for constant current electrolysis, it consists of a suitable cell and a direct current source. A 6 volt storage battery can be used for DC power source. An ammeter and voltmeter are used to indicate the current and applied voltage respectively. The voltage applied to the cell, it is controlled by a resistor, and the cathode taken, that is usually a platinum gauge. So what is the physical characteristics of the metal deposits that occur during this process? So it is important that the deposits produced by electrolysis, it should be pure, strongly adherent, dense and smooth, so that it can be washed, dried and weighed without any mechanical loss. So spongy, powdery or flaky deposits, they are likely to be less pure and less adherent. So as mentioned earlier, the principal factors that influence the physical characteristics of deposits are current, density, temperature and the presence of complexing agents. So stirring generally improves the quality of a deposit. So during the process, stirring should be frequently done. It should be performed throughout the process. The time of deposition is reduced when the solution is stirred vigorously or if the electrode is rotated at a uniform speed. So this type of stirring, it lowers the concentration over potential and enables a higher current density without any adverse effect. Simultaneous evolution of gas at an electrode during deposition, it is not desirable. So porous and spongy deposits are obtained if there is gas that it evolves during the process. So the chemical nature of the ion in solution, it also has an important influence on the physical form of the deposits that is obtained. So, for example, if we take a pure and bright adherent deposit of copper, it can be obtained by electrolyzing nitric acid solution of cupric ions. But in contrast, a coarse deposit of silver is obtained under the similar conditions. So, that is why this process is also dependent on the nature of the material that is being electrolyzed. The electrolysis from a solution of silver cyanide complex, it produces a very good deposit. Complex ions, they have a property known as throwing power, that is by virtue of which the deposit is made on irregular surfaces. So increase in temperature also it favors diffusion, but if the hydrogen over potential is decreased and the stability of many complexes is decreased. So in practice, constant current electrolysis is limited to the separation of an easily reduced cation from cations that are more difficult to be reduced than hydrogen. Now, potential changes during an electrolysis at constant applied potential. So here in figure 5.6a, it is the current and IR drop and cathode potential change during the electrolytic deposition of copper at a constant applied cell potential. So what happens is, if we consider the electrolysis of copper 2 plus ions in acidic medium. So initially what happens is, the applied potential to the cell is about minus 2.5 volt, which leads to a current of 1.5 ampere. Here it is shown in figure 1.5a. 5.6a. The electrolytic deposition of copper is then completed at this applied potential. As the reaction proceeds, the IR decreases continually. Now, this decrease occurs because of the concentration polarization at the cathode, which limits the rate at which copper ions are brought to the electrode surface, and thus the current is limited. The decrease in IR, it must be compensated by an increase in the cathode potential since the cell potential is constant. The increase in cathode potential is slowed down at point B by the reduction of hydrogen ions. Since the solution contains large excess of acid, the current is no longer limited by concentration polarization, and co-deposition of copper and hydrogen goes on simultaneously until all the copper ions are deposited. So again, let us consider a case in which a solution of copper 2 plus and Pb2 plus ions are present. The Pb2 plus ions, they begin to deposit at point A or on the cathode potential curve 5.6b. So here in this figure, the at the point A, Pb2 plus ions, they start getting deposited. Hence, lead 2 ion would co-deposit before the copper deposition is complete, and thus it will interfere. Now, co-deposition of hydrogen during electrolysis, it often leads to spongy and very flaky deposits. So such a situation is not required and it is unsatisfactory. So the use of depolarizers, they have been used for such type of processes. A depolarizer is a substance which gets reduced at the cathode without gasification or gets oxidized at the anode before oxygen evolution and stabilizes the potential of the working electrode by minimizing the concentration polarization. Thus, the copper which is deposited from a nitric acid solution, it is smooth and adherent because the nitrate ions, they act as depolarizers. The cathodic depolarizer, nitrate ion, it gets reduced at a potential less negative than at the point C, here as it has been shown. Nitrate ions have long been used in the constant current deposition of copper and lead, wherein copper is deposited at the cathode and lead is deposited as lead oxide at the anode. So here in table 5.1, the typical applications of constant current electrolysis, it has been shown. Like for example, if the analyte is Ag plus, then the cathode is platinum cathode, anode is platinum cathode, and the conditions is that alkaline cyanide solution should be taken. Then these are the various parameters that we need to maintain for different for constant current electrolysis of different types of analytes. Then coming to constant potential electrolysis. So by constant potential electrolysis, it is possible to separate two elements whose deposition of potentials differ sufficiently. The potential of the cathode is controlled so that it never becomes sufficiently negative to allow the deposition of the next element. As can be seen from figure 5.6b, the potential of the cathode, it becomes negative due to concentration polarization, and that co-deposition of the other species, it begins before the analyte is completely deposited. A large negative drift in the cathode potential can be avoided by using a 3 electrode system, here as it is shown in figure 5.7. So the apparatus for controlled potential electrolysis. Contact C, here it is adjusted, and that is according to the work setup. The controlled potential electrolysis consists of two independent electrode circuits that share a common electrode, that is the working electrode at which the analyte is deposited. The electrolysis circuit consists of a DC source, a potential divider that permits continuous variation in the potential applied, and the working electrode and the counter electrode. The reference circuit, it consists of the standard electrode, that is uh, standard calomel electrode, a high resistance digital voltmeter, and the working electrode. The electrical resistance of the reference circuit is so large that the electrolysis circuit supplies essentially all the current for the deposition. The purpose of the reference circuit is to monitor continuously the potential between the working electrode and the reference electrode. When this potential reaches a point at which co-deposition is about to begin, then the potential across the working and counter electrode, it is decreased by moving by the knobs. Since the potential of the counter electrodes remains constant during the change, the cathode potential becomes smaller, thus preventing co-deposition. Now here in figure 5.8, illustrates the changes in cell potential and current during a controlled cathode potential electrolysis of copper. The applied cell potential has to decrease continuously throughout the electrolysis. This decrease in turn, it diminishes the current. Completion of the electrolysis will be indicated by the approach of the current to zero. This technique demands constant attention during operation. So then coming to electrodes. So usually platinum gauge electrodes, they are used because they have the advantage of being non-reactive and inert, and they can be ignited to remove any organic matter or gases that have harmful effect on the physical properties of the deposit. Certain metals like bismuth and zinc, they cannot be directly deposited on platinum since they permanently damage the electrode. Hence, a protective coating of copper is always deposited on the platinum electrode. Then the mercury cathode. Mercury cathode is particularly useful for removing easily reducing metals such as a preliminary step. For example, copper, nickel, cobalt, silver, and cadmium, they are readily separated at this electrode from ions like aluminium, titanium, alkali metals, sulfates, phosphates, etc. The precipitated elements, they dissolve in mercury with little hydrogen evolution because mercury has a very high hydrogen overvoltage, and hence no hydrogen evolution even at high applied potential occurs. So what are the advantages of mercury cathode? The first is it forms an amalgam with a number of metals. The second is it has a high hydrogen over voltage, and hence no hydrogen evolution occurs even at very high potentials. So what are the applications? The controlled cathode potential is very useful in the separation of quantitative determination of metallic species. So how is this helpful? First is the successive deposition of metals. Suppose we take a mixture of copper, bismuth, lead, cadmium, zinc and tin. Then this mixture, it can be determined by the successive deposition of the metals on a platinum cathode. First, copper is deposited by maintaining the cathode potential at minus 0.2 volt versus SC. After weighing the cathode, the copper plated cathode is used to deposit bismuth at a potential of minus 4 volt. Then lead is deposited over the same cathode by maintaining a cathodic potential of minus 0.6 volt. So all the three elements, they are deposited from neutral solution containing tartarate ions, which forms a complex with tin. So likewise, all the solution, it is finally the solution is acidified, and then we can use a fresh electrode. So simultaneous depositions, a mixture of copper and lead can be determined by the deposition of copper in the presence of nitrate at the cathode. Lead is deposited at lead dioxide at the anode. Another application of constant cathode potential is in preparative organic chemistry. So, if an organic compound can undergo a series of reductions or oxidations, each at a definite potential, then it is possible to reduce the starting material to the desired product by controlling the potential of the cathode during the reduction. This type of electrolytic reduction, it is much more economical than chemical reductions. So in table 5.2, applications of controlled cathode potential electrolysis has been used for Cu2 plus. The cathode is platinum, and the condition that should be maintained is sulfuric acid HNO3 solution. Similarly, for identification of separation of silver, platinum cathode should be used, and the condition should be 10% KCl. So potassium cyanide. So by employing the by different conditions, we can identify different types of compounds. So now we'll start with coulometry. So before starting with coulometry, we'll just take a break of 5 minutes and then again resume. So now we'll start with coulometry. This is another important electroanalytical technique. So coulometric methods, they are based on the measurement of quantity of electric charge that passes through a solution during an electrochemical reaction. Now electrogravimetry, that measures the amount of the substance that is deposited during the process of electrochemical reaction. But in coulometry, it measures the amount of the electrical charge, the changes in the amount of the electrical charge that occurs during the electrochemical reduction reaction process. So the principle of coulometric method is governed by Faraday's laws of electrolysis. Now Faraday conducted several experiments and he found out a series of law. Today both they are called as Faraday's first law of electrolysis and Faraday's second law of electrolysis. So, according to the first law of electrolysis, Faraday's first law, the mass of a substance that is liberated at the electrodes during the electrolysis process is directly proportional to the quantity of electrical charge Q that is passed through the electrolyte. If M is the mass of a substance deposited by current of I amperes in T seconds, then according to this law, M is directly proportional to Q or M is directly proportional to I into T. So overall we can write M is equal to Z I T. So here Z is the proportionality constant. So from the first law, we see that it relates the quantity of the current and the extent of the chemical uh, change that takes place in the reaction. Then coming to the Faraday's second law of electrolysis, the mass of different substances that is either evolved or deposited by the passage of same quantity of electricity, it is proportional to their chemical equivalence. That is, M is directly proportional to m1 by n. So here mr by n. So here m is the mass of the substance, mr is the molar mass of the substance that is liberated or deposited, and n is the valency. So if m1 and m2 are two different masses of two different substances, then we know that m1 n1 by capital M1 is equal to m2 n2 by capital N2. Like one example has been solved here. For example, let us consider the passage of electricity through solutions of copper sulfate and AgNO3 that is connected in series, so that the same amount of electricity is passed through them. Then from the second law, we see that mass of the copper deposited into 2 by molar mass of copper is equal to mass of silver deposited into 1 by molar mass of silver. Now where does this 2 come from in mass of copper deposited? That is the valency of copper, and that is Cu2 plus, which requires two electrons. Then the mass of, since we have taken AgNO3, then the valency for silver ions, that here it is taken as 1. So the quantity of electricity or charge, it is equal to the product of current strength or charge and time for which the current is passed. That is, Q is equal to current into time, that is I into T, and the practical unit of electricity is coulomb. So when a current of 2 ampere, it flows for 10 seconds, then the Q, that is the quantity of current, it is given as we know I into T. So here I is equal to 2 ampere and the T is equal to 10 second. So we get 2 into 10 ampere into seconds, that is 20 coulomb, since the unit of electricity is coulomb. Now for a variable current, the I the electricity. So let us understand the term Faraday. So what is how a Faraday, one Faraday is defined? The quantity of electricity that is carried by 1 mole of electrons is called Faraday, and it is given by the symbol F. The charge of an electron is 1.6022 into 10 to the power minus 19. Hence, the charge on 1 mole of electrons would be 1.6022 into 10 to the power minus 19 into the Avogadro's number, that is 6.022 into 10 to the power 23, and that overall becomes 96485 coulombs. So approximately we can write 1 Faraday is equal to 96500 coulomb. So this is the overall representation of 1 Faraday of, that is, one capital F is written as 96500 coulomb. So now let us consider a reaction. So first is the Mn plus, that is the ionic form of the metal N plus. It takes up N electrons to form the metal M. So the quantity of electricity that is required for the deposition of 1 mole of an element, it will be equal to N into F. So where, why N? So here this N, it represents the number of the moles of electrons required for the reaction. Now suppose the molar mass, that is Mr, it will be given. We know that Mr, we require N, the small molar mass, this is the small M, will be given as capital Mr into Q by 96500 into N grams. Now we will simplify this equation, and we get that M is equal to Mr into I into T by 96500 N. So this equation, this is helpful in calculating the mass of an element that is deposited by the passage of a known quantity of current. So small n can always be the mass that is deposited, it can be calculated from this equation. Then coming to what is a coulometer. So a coulometer, it is a device that is used for measuring the quantity of electricity that is required to bring about a chemical change of the analyte. So it is usual practice in coulometry to substitute the ammeter with a coulometer. So each coulometer is a second electrolytic cell in which the anode and cathode, they may be used in the same compartment or in separate compartment, supposed to proceed at 100% current efficiency. It is put in series with the electrolytic cell so that the same quantity of electricity it passes through both the cells. Various types of coulometers are present, like gasometric coulometers, hydrogen oxygen coulometer, gravimetric coulometers, silver coulometers, titrimetric coulometers, and iodine coulometers. So we'll discuss a few of them. First is the gasometric coulometers, or we call them as the hydrogen oxygen coulometers. So in these coulometers, here the figure 5.10, it has been, the simplified diagram has been shown. The hydrogen oxygen coulometer, it consists of a glass tube of about 50 centimeter long and a diameter of 2 centimeter. Two platinum sheets of about 1.5 square centimeter, they are joined with a stout platinum wire that serves as the electrodes. A calibrated tube is connected to the electrolysis tube by means of a pressure rubber tube, and it is capable of moving vertically so as to adjust the pressure of the collected gases to atmospheric pressure before measuring the volume of the gases. So as the electrolyte, we take 0.5 molar of potassium sulfate. So the electrolytic reaction that occurs at the anode is given as, is the evolution of oxygen, and at the cathode hydrogen is evolved. So the overall reaction for the cell reaction, it can be given as 2H2O giving 2H2 plus 2. So 3 moles of gases, that is 2 moles of hydrogen and 1 mole of oxygen, are produced by consumption of 4 Faradays, which is equivalent to 0.17 centimeter cube at NTP of a mixed gas per coulomb. Now Lingen and Leffield, they found the actual volume to be 0.1739. So such coulometers, they show an accuracy of about minus 0.1%. So they are highly sensitive in nature. So it has been reported that the loss of efficiency is due to the formation of hydrogen peroxide at the anode, which aggravates the situation by being reduced at the cathode. So the cathodic current efficiency also suffers. The other common gasometric coulometer is the hydrogen nitrogen coulometer. So the cathodic reaction, so the anode reactions is given as N2H5 plus, giving rise to N2 plus 5H plus 4E. The cathodic reaction is 4H plus 4E, giving rise to 2H2. The overall reactions can be given by the evolution of N2 and H2 plus H plus. So if we look into the total number of moles, we see 1 mole of nitrogen and 2 moles of hydrogen. That is total 3 moles of gas. They are produced by consumption of 4 Faradays, and the yield is theoretically again 0.1741, and it has been found to be 0.1738 ml. So we see that even this hydrogen nitrogen coulometer is also as sensitive as the hydrogen oxygen coulometer. So these are some of the these two are the two very precise coulometers that are being used today. So there are some precautions that need to be adopted while using those hydrogen oxygen coulometer. The first is the gas burette should be water jacketed, and the temperature should be within zero point 0.1 degree centigrade. The electrolyte must be pre-saturated with oxygen and hydrogen mixture, and during the course of the reaction, the gas burette must be lowered periodically to hold the gas pressure close to atmospheric pressure so that the solubility equilibrium is maintained. Now coming to silver coulometer. So a silver coulometer is an example of a gravimetric coulometer in which the amount of metal deposited at the cathode or the amount of metal stripped from the anode is determined. A silver coulometer, it has been shown here in figure 5.11. It is the most satisfactory either in the cathodic deposition mode or in the anodic stripping mode. So a convenient silver coulometer, it consists of a platinum disc or silver disc which acts as a cathode and contains a solution of 1 molar silver nitrate as the electrolyte. A rod of pure silver enclosed in a porous pot, it acts as the cathode, and 1 mg of silver, and this should be considered with reference as the reference electrode. So after electrolysis, the cathode is weighed. The increase in mass of the cathode, it gives the amount of the silver deposited. So from the increase in mass, and we can calculate the number of Faradays that is involved. So then iodine coulometer, it is an example of a titration coulometer in which anodically generated iodine, it is titrated with thiosulfate or arsenic solution. This has been used in the determination of Faraday constant. Then coming to colorimetric coulometers. So these are based on the principle of developing a colored species with a reagent with a metal ion that is to be anodically stripped. So for example, the formation of a colored species of cobalt ion with nitroso R salt and measurement of absorbance with a spectrophotometer. A metal ion may be cathodically reduced and subsequent absorbance may be measured. For example, reduction of iron 3 at the cathode and subsequent measurement of absorbance with 110 phenolphthalein reagent. Then coming to radioactivity coulometers, a microcoulometer that is based on counting deposits of silver 110 has been described. So the unknown silver solution, it is spiked with a known amount of radioactive silver 110, and then it is made to deposit on a platinum wire where one part contains only the radioactive silver. Equal amounts of silver, they are plated on each electrode. The ratio of the radioactivities, it gives the amount of the silver in the unknown solution. So this method, it is useful for for determination of very small quantities. So now coming to types of coulometric methods. So coulometric methods, they are divided into two types. One is called as the constant current coulometry, or we call it as amperostatic coulometry. The second is the controlled potential coulometry, that or we call it as the potentiostatic. This amperostatic coulometry is further divided into two classes. One is the primary and secondary coulometric analysis. The secondary coulometric analysis is further divided into external generation and internal generation, whereas the potentiostatic coulometry is just further classified as primary coulometric analysis. Now we'll start with constant current coulometry, that is amperostatic coulometry. So in constant current coulometry, the current is maintained constant till the completion of the analytical reaction, which can be detected by visual indicator or solution. The quantity of electricity required to attain the endpoint is derived from the amount of coulombs consumed. So primary constant current coulometry, the estimated the element to be estimated, it undergoes direct reaction at the electrode with 100% efficiency. Secondary constant current coulometry. This method has enjoyed wider applications and is frequently called a coulometric titration. So, in a coulometric titration, one of the reactants or titrants is quantitatively produced at an electrode, which then stoichiometrically reacts with the analyte ion to be estimated. So, a titration of, for example, a titration of ferrous ion versus ferric ion. It is an example of a coulometric titration. So considering the oxidation of iron 2 at the platinum anode, the primary anodic reaction, we can write it as Fe2 plus, that is forming Fe3 plus electrons. So in constant current electrolysis, towards the completion of the reaction, there is an increase in the applied cell potential. Because of the concentration polarization, the increase in cell potential, it causes the anode potential where the water decomposition takes place. That is, H2O breaks down to O2 plus 4H plus 4E. So hence the completion of the reaction, that is oxidation of iron at platinum anode, it is not achieved. But the current efficiency of this process is becomes it less than 100%. So coulometric titrations, they are more popular because of the in situ generation of titrimetric reagents. Like for examples, the halogens have been found to be most satisfactory coulometric intermediates in coulometric titrations. The reactions with electrolytically generated bromine and iodine, they are useful for the estimation of substances like oxime and ascorbic acid. Now coming to potentiostatic coulometry. So here in potentiostatic coulometry, the potential of the working electrode, it is kept constant. So quantitative oxidation or reduction of the analyte, it can occur. The current is initially very high, but it decreases rapidly and approaches zero at the completion of the reaction. So the quantity of electricity is most commonly measured with an electronic integrator or from the reading of a coulometer in series with the cell. So special features of coulometric methods, the coulometric methods, they give more accurate and precise results than classical methods, since the electrical currents can be controlled and measured with utmost precision. These methods are suited for both routine as well as rare analysis, uh, which involve electrolytic method of determination. Coulometric titrations, they are more popular and have the special advantage in the sense that the tedious step of preparation, storage and handling of standard titrants are avoided. Titrations which cannot be performed by conventional methods can be easily performed by coulometry. So titrations of hazardous materials or unstable materials can also be performed by coulometry. In situ generation of titrants, like for example, electrolytic generation of iodine used to estimate hydroquinone, ascorbic acid, antimony, electrolytically generated bromine used to estimate organic substances like oxime have been found to be very satisfactory by this method. Constant current coulometry, that is the amperostatic coulometry, has been widely used than potentiostatic coulometry because it is faster and requires simpler instrumentation and it is less expensive. Controlled potential coulometry is quite sensitive and has very high selectivity. So now coming to the principle of potentiostatic coulometry. So, to begin with, in potentiostatic coulometry, the potential of the working electrode is constant because this technique is similar to electrogravimetric method where electrolysis is carried out at a fixed potential. However, so controlled potential technique can there is applied to system that yield deposits with poor physical properties. So the instrumentation, it consists of a potentiostat to maintain a constant potential, an electrolysis cell, a chemical coulometer, or an integrating device for determining the number of coulombs and placed in series with the working electrode. The chemical coulometer, such as hydrogen oxygen coulometer, silver coulometer, can be used to measure the number of coulombs. Cell assembly. The cell assembly consists of a platinum gauge working electrode, a platinum wire counter electrode, and a saturated canonical electrode, which is called as the reference electrode. The counter electrode is separated from the test solution by a porous tube containing the same supporting electrolyte. Here in figure 5.12a it has been shown. So here in the first case, the electrolysis cells for potentiostatic coulometry, the working electrode in the first case is the platinum gauge, and in the second case it is a mercury pool. So sometimes mercury is also used. The cell here, mercury can also be used as it has been shown in figure 5.12b. So this cathode is useful for separating the easily reducible elements during an analysis. For example, copper, nickel, cobalt, silver and cadmium, they are easily separated from ions such as aluminium, titanium, alkali metal and phosphates. The precipitated elements dissolve in mercury and they form amalgams. Potentiostat is an electronic device which maintains the potential of the working electrode. So figure 5.13 is a schematic diagram of a potentiostatic coulometry. So in this is a figure diagram how a potentiostatic coulometry it works. So the potentiostat will consider the circuit figure 5.13 of the diagram. The two resistance of the diagram, they respond to resistances in two parts. Here the RS in the cell, it is the resistance between the counter electrode and the tip P. RU is the uncompensated cell resistance, in which cell resistance between P and working electrode. So if we consider the path between the inverting input and the circuit, we see that E2 here in the cell, E2 can be given as E1 is equal to ESC plus ICRU plus ESC plus EC. So here EC represents the cathode potential. So during the process of electrolysis, if the resistance of the unknown uncompensated cell and RS it changes, then the operational amplifier output also changes. So if RU changes as a result of the increase in SAR cell resistance or due to concentration polarization, the output voltage also decreases, which leads to a decrease in IC. So the practical circuit here, it shows the basic components of a potentiostatic coulometry. The circuit includes a variable voltage source at the non-inverting input of the operational amplifier so that the potentiostat control potential can be varied, and a booster amplifier to supply the high currents. Then comes the integrators. Most of the modern apparatus for potentiostatic coulometry, they employ integrators to determine the number of coulombs required to complete an electrolysis. Efficient stirring is important for controlled potential electrolysis because all analysis species must be swept up to the electrode surface so that the electrochemical reaction is completed. Besides stirring, the ratio of the electrode surface to surface volume is another requirement of the experiment. This ratio plays a role in determining the time needed for complete electrolysis. Since the electrical current will be directly proportional to the electrode area and also directly proportional to the concentration C of the analyte, we can write I is directly proportional to C into A. We know that Q is equal to I into T. So this implies this Q is equal to I into A is directly proportional to C into A into T. So this is how we the overall dependence of different factors in potentiostatic coulometry. So coming to the applications of coulometry, uh, first is in inorganic analysis. Now, controlled potential coulometric methods, that is the potentiostatic coulometry, it has widespread use in the determination of several metal ions. So, as many as 55 elements of the periodic table, they can be determined by this cathodic reduction. So, it is also used in analysis of radioactive metals. This technique is also widely reported for the deposition of uranium and plutonium, and it finds extensive use in the field of nuclear chemistry. So reduction of UO2 2 plus to and to U4 plus. It can be carried out in H2SO4 medium with a mercury pool cathode. Microanalysis controlled potential coulometry is more popular than the electrogravimetric methods since it avoids the final step of weighing the product. Multi-step controlled electropotential electrolysis, determination of several metal ions in the same solution is possible with controlled potential electrolysis using mercury pool cathode. A sample solution containing several metal ions such as copper 2 plus, bismuth 3 plus, lead 2 plus, Zn 2 plus, they can be analyzed by controlled potential analysis. So when the current decays to zero, then the potential can be controlled so that bismuth 3 plus can be reduced to bismuth 0 plus. Subsequently, by controlling the potentials, Pb2 plus can be determined as Pb0 and Zn2 plus as Zn0. So continuous monitoring of gas stream, determination of trace level concentration of oxygen in a gas stream can be done by controlled potential reactions. The cell consists of a porous silver cathode and a cadmium anode. The reactions are O2 plus H2O4e forming 4H plus and CDS plus 2OH minus forming CDOH whole 2 plus gain of 2 electrons. So the porous silver cathodes, they serve to break up the incoming gas into small bubbles wherein the reduction of oxygen takes place quantitatively within the pores. The hydroxyl ions that is formed during the reduction reaction, it reacts with the cadmium anode and forms a cadmium hydroxide solid product. So here in figure 5.14, an instrument for continuously recording the oxygen content of a gas stream, it has been shown. So a special feature of this setup is that the galvanic cell is formed and hence no external power supply is needed. There is no need of a potential stat to control the potential of the working electrode. The current produced is passed through a standard resistor and the potential drop is recorded. The oxygen concentration is proportional to this potential and a digital display can indicate the oxygen concentration directly. The setup can be used for determination of oxygen in any gas stream and can detect oxygen concentration from 1 ppm to 1%. Then coming to electrolytic determination of organic compounds. Now potentiostatic coulometry, it offers a new step for the electrolytic determination for the electrolytic determination of organic compounds. Trichloroacetic acid, that is TCA, and picric acid, they are quantitatively produced at a mercury cathode. So coulometric methods permit the analysis of they permit the analysis of these compounds with an accuracy of almost 0.1%. That is here the equation, it has been shown. Electrolytic synthesis of new organic compounds, synthesis of new species and novel chemical compounds are possible. No chemical reagents are required since electron itself is the reagent of carrying out these reactions. No contamination of the products takes place. Then determination of n values of the reaction. Controlled potential coulometry can be used to determine the n values of the reactions. Determination of n values, it offers a route to deduce the kinetics and mechanism of the overall reactions. Picric acid is reduced at a mercury pool cathode in which n value of the reaction was found to be 18. Now the reaction product is identified to be triaminophenol. So this is how it helps in the determination of the n value of a reaction. Now coming to amperostatic coulometry. So this technique is better. It is called as coulometric titration. So in a coulometric titration, the titrant is generally, it reacts stoichiometrically with another and it proceeds with 0% efficiency. It involves a single change in the analyte. Coulometric titration, there has a special advantage in the sense that a standard solution is not required. This, because a standard solution is not required, it can be used for the determination of estimation of micro and semi-micro quantities of substances. So here in figure 5.15, it depicts the major components of a typical coulometric titrator. A source of constant amperostat, here it is and a switch that is simultaneously that initiates the current. and starts an electronic timer are required. The potential drop across the standard resistor, it is used for the measurement. Many electronic or electrochemical amperostats, they are also easily available in the market. So now coming to the cell assembly. So here in the cell assembly, so here in the cell assembly, we can see that it consists of a generator electrode at which the titrant reagent is generated and a counter electrode to complete the circuit in figure that has been shown in figure 5.16. The generator electrode is a platinum foil or gauze with a large surface area. The products formed at the secondary electrode, normally it interfere with the electrochemical reaction. For example, the anodic generation of oxidizing agents, that is conversion of Ce3 plus to Ce4 plus, is often accompanied by the evolution of hydrogen from the cathode. This hydrogen, it reacts with the oxidizing agent and leads to a positive error. Hence the electrode is isolated from the test solution by a sintered glass discs. Beside, this type of arrangement helps to maintain 100% efficiency. Now, external generation of titrant. Since internal generation of titrant sometimes it interferes with the titration process, it becomes necessary to generate the titrant externally and to deliver it to the reaction cell. So, an assembly has been shown in figure 5.17. The hydrogen and hydroxyl ions, they are produced by the electrolysis of sodium sulfate ions here, and the cell consists of two electrodes of platinum gauge separated by a sintered glass. The anode of the compartment produces H plus while the cathode produces OH minus. The apparatus is so arranged that the flow of electrolyte, it continues even after the current is discontinued. Now, this type of external generation apparatus has also been used for the generation of other reagents such as iodine by oxidation of iodine at the anode, generation of titanious ions, and etc. It should be noted that external generation of reagents is possible if only the titrant be generated with 100% current efficiency. So, detection of endpoints in coulometric titration. Detection of endpoints which indicators, as in case of volumetric titration, it is quite satisfactory. For example, detection of endpoints with starch indicator in titration. So it is against electrically generated bromine. However, coulometric endpoint can be accurately determined by instrumental methods such as potentiometric, conductometric, amperometric, or photometric methods. Potentiometric endpoint has been found to be suitable in acidimetric and redox reactions. So this method of detection of the endpoint has the advantage that the titrations can be stopped exactly at the endpoint. Besides, the observed EMF does not depend on factors like geometry of the cell, conditions of the stirring, and etc. So thus these methods of detecting the endpoints, they are much more advantageous and they are much more sensitive. Amperometric detection of endpoint is useful in redox and precipitation titrations and is still more advantageous than potentiometric method of detection of endpoint because the choice of the indicator electrode for detecting the endpoint does not depend on the availability of reversible indicator electrode. Even if one of the ions is electroactive, the endpoint can be detected quite easily. So, spectrophotometric endpoint detection has been developed in recent years. This is of great importance in the titration of olefins with electrolytically generated bromine. Some of the special advantages of this method are the exact endpoint can be determined by the extrapolation of the linear portion of the titration curves before and after the endpoint. By proper choice of lambda max and molar absorptivity, the sensitivity and selectivity of the methods can be improved. So now coming to applications of coulometric titration. Coulometric titrations have been developed for all types of volumetric titrations. Some important applications of coulometric titrations are given below. Like for one is the neutralization reaction. The titrations of strong acids or weak bases with hydroxide ions, they generated at the cathode have been developed. So the cells that have been shown in the above figure, they can be used to generate hydroxide ions. Endpoints can be detected by the use of indicators. However, potentiometric endpoints can also be employed depending upon the availability of the instruments. A real advantage of such coulometric titration is that interference from carbonate ions can be avoided by the generation of hydroxide ions. Those are free from the carbonate ions. However, it is necessary to de-aerate the solution which with an inert gas before beginning the analysis to avoid the interference of carbonate ions. So the titrations of strong or weak bases are possibly with hydrogen ions generated at the platinum anode. Then coming to precipitation and complex forming titration, a large number of coulometric titrations have been developed with the anodic generation of silver ions. The generator electrode consisting of a heavy silver wire, it can be constructed and a cell of the type can be shown. Endpoints can be detected with adsorption indicators or by potentiometric methods. Similar titrations that have been based upon the generation of mercury 1 ion at mercury anode have been described. So complexometric titrations using EDTA ions Hy3 minus generated at a mercury cathode have been developed for the titration of several cations. Reduction of the amine mercury EDTA chelate at the mercury cathode has also been used to generate Hy3 minus. Since mercury chelate is much more stable than the corresponding complexes with calcium, zinc, lead or copper, titration of these cations they are possible by this method. Then the next application is in redox titrations. So the oxidizing reagents such as iodine, bromine, chlorine, Ce4 and the unusual uh, oxidation states of certain ions like silver 2 plus, Mn3 plus, uranium 4 plus can be generated by making use of coulometric titrations, and the use has been listed in table 5.3. So coulometric titrations of redox titrations they assume importance because of the possibility of in situ generation or unusual unstable reagents such as bromine, depositive silver ions, dipositives, tripositive manganese, etc. Conventional volumetric analysis they cannot handle these reagents. The electrogenerated bromine has been proven to be very useful for the determination of phenol, aniline, mustard gas, etc. A bromine solution is quite unstable and cannot be used as a titrant in conventional volumetry, and then one has to use Winkler's solution to carry out such reactions. So, however, these limitations they are ignored by the use of coulometric titrations. Here in table 5.3, the application of coulometric titrations that involve neutralization, precipitation, and complex forming reactions it has been shown. So, for determining acids, the generator electrode reaction is the 2H, H2O giving rise to 2OH minus plus 2H2, and the secondary analytical reaction is OH minus forming H2O. So table 5.4 shows some of the applications of coulometric titrations involving the redox reactions. Like if the reagent is bromine, then the generator electrode reaction is Br minus forming Br2, then the substance to be determined is can be phenol, mustard gas, aniline, etc. For if the reagent is Cl2, then the substance that can be determined is arsenic 3 iodide minus. So likewise, these are some of the applications of colorimetric titrations in that involve redox reactions. A list of other applications involving other ions has been shown here. Then coming to the advantages of coulometric titrations, the preparation, standardization and storage of standard solutions, they are not necessary in coulometric titrations. This is useful especially for preparation of unstable reagents such as dipositive silver ions, tripositive manganese ions, bromine, chlorine, titanium, etc., which can be generated in situ. Since the conventional method they cannot handle this type of reagents. It is easy to handle small quantities of reagents by coulometric titrations by proper choice of current, micro quantities of by proper choice of current micro quantities of substance they can be analyzed with greater accuracy and ease. A single constant current source can be used to generate precipitating, complexing and redox reagents. Coulometric titrations can readily be adapted to automatic titrations as the current control is easily done. A number of automatic coulometric titrators, they are readily available in the market to monitor environmental pollutants. In chloride titrator, silver ion is generated coulometrically. In sulfur dioxide monitors, anodically generated bromine oxidizes the analyte to sulfate ions. In carbon dioxide monitors, in which the gas stream absorbed is monoethanolamine, it is titrated with coulometrically generated base. So in water titrators, Carl Fisher reagent is generated electrolytically to determine trace level concentrations of water content or moisture. So these are some of the applications of coulometric titrations. So with this, the it today's unit on electrogravimetry and coulometry, it is finished. So these are some of the terminal questions and answers associated with this chapter. So we'll take a break of 5 minutes, and then again we'll resume with a new chapter. So, in this chapter, we'll talk about the applications of conductometry, electrogravimetry, and the coulometry. So, in previous units, we have talked about the applications, the principles, the instrumentations. So in this chapter, we'll just discuss about their different applications. So first is the application of conductometry. So first on the conductometry, we will just, before understanding, we'll understand that what do you mean by degree of dissociation of weak electrolytes and dissociation constant. So we know if we take a weak acid HA, it will dissociate to form H plus and OH minus. If the initial concentrations are C00, then at equilibrium concentration, then the at equilibrium the concentration is given as C into 1 minus alpha into C alpha, and the A minus is C alpha. So alpha is here the degree of the dissociation. So then the thermodynamic equilibrium constant, that is Ka, it can be written as concentration of H plus into A minus by concentration of Ha. Now put substituting all the values from equation 6.1, we see that Ka is equal to alpha square C by 1 minus alpha. Now this equation 3.3, it is called as Ostwald's dilution law. Similarly, for a weak base, we can write Kb is equal to alpha square C by 1 minus alpha. So now if we let us consider a very uh, salt with a very partial dissolution or low solubility Ma. So it will give us to, it will break to form, dissociate to form Ma, forms M plus A minus. The equilibrium constant Ks, it can be written as activity of M plus into activity of A minus divided by activity of the salt Ma. Now since this salt is taken in solid form, therefore the activity of Ma is equal to 1. So therefore the Ks, that is the equilibrium constant, now changes to activity of M plus into activity of A minus, and this Ks, it is called as your solubility product. So this is the basic concept in the dissolution of weak acid, weak base. So now, using all this Ka, Kb and Ks value, Ostwald derived a relationship between the molar conductivity and limiting molar conductivity. The molar conductivity of a weak electrolyte, it can be expressed as the product of degree of dissociation and of the electrolyte and its limiting molar conductivity. That is, lambda m is equal to alpha into lambda to the power alpha, or we can write alpha is equal to lambda m by lambda to the power alpha. So this relationship is known as Ostwald relation. So which on rearranging we find out that alpha Ka, that is here lambda mc is given as Ka into lambda alpha to the power square by lambda m minus Ka by lambda alpha. Now if we plot lambda mc versus 1 by lambda m, we get a plot with slope equal to Ka into lambda alpha to the power square. So here in table 6.1, the molar conductivity values of nitric acid in methanol, it has been shown, and this is the plot of lambda m versus 1 by lambda m. So here if we see, this is a graph, is a straight line, the slope is Ka into lambda alpha to the power square, lambda alpha to the power whole square, and substituting the values, the Ka, it can be known. But in the case of a very weak electrolytes, it is not possible to obtain the lambda limiting molar value. So by extrapolation, so for such weak electrolytes, instead we use Colrat's law. Now from Colrat's law, we know that lambda CH3COH, it can be written as lambda CH3CONA plus lambda HCl minus lambda NaCl. Now in the right hand side, we can see these are all the values of the strong electrolytes. So the value for molar conductivity at infinite dilution for all the three electrolytes, they are known. Substituting the values, we can find out the molar conductivity, the limiting molar conductivity for lambda CH3COH. So and this is how it is useful. So if the molar conductivity of a particular solution is known, then its degree of calculation, degree of dissociation can be calculated as alpha is equal to lambda m by lambda to the power infinity. So to calculate the dissociation constant Ka, we can use the formula alpha square C by 1 minus alpha. So this is some of the general basic equations. Then coming to ionic product of water. So to know the ionic product of water, we see the dissociation of water to H plus and OH minus, and the equilibrium constant is Kw is equal to AH plus into AOH minus, forming the activity of water. Now the activity of water is 1, then for pure water is 1. So therefore the ionic product, that is Kw, it now becomes activity of H plus into activity of OH minus, or that we can write concentration of H plus into concentration of OH minus. So here Kw is called as the ionic product of water, and it can be determined from as follows. It has the value, it has been found to be 0.4. Can be found by this process, that is CH plus is equal to COH minus and C, and then the accepted values at infinite dilution has been found to be this. So the calculate we can, using this equation 4.8, we can calculate the concentration of hydrogen ions to be this here, which has been found to be 5.8 into 10 to the power minus 6 Siemens per meter at 298 K. Since the of activity coefficient of ions in pure water, it cannot differ appreciably from unity. This result is very close to Kw. So we see here the conductivity and ionic product of water at different temperatures. It has been shown, and they are almost we can see the difference in their values. Then coming to solubility and solubility product of a salt. So we know that the K salt, the conductivity of a saturated solution of a sparingly soluble salt, it is determined by subtracting the conductivity of the solution from that of the pure solvent. That is, kappa of the salt is equal to kappa of the solution minus kappa of the solvent. So the molar conductivity is given as lambda salt is equal to kappa of salt by C. Also, we know that lambda of salt is equal to lambda infinity dilution positive of the ion, and lambda to the infinite dilution of the negative ion. So here C is equal to kappa of salt by lambda plus and lambda minus. So the limiting ionic conductivities, it can be obtained from the literature, and then substituting the values we can know after. Once we know the value of C, then we can find out the KSP, that is the solubility product. So here one example has been shown how to calculate that for HCl. For AgCl, the limiting molar conductivity of its ions are Ag plus Cl minus, and it has been given. So the conductivity has also been provided, and then using the above values, we can find out the KSP, that is the solubility product. So now coming to conductometric titrations, the principle of conductometric titration, it is based on the fact that during the titration, one of the ions is replaced by the other, and invariably these two ions, they differ in the ionic conductivity, with the result that conductivity of the solution, it varies during the course of the reaction. So in order to reduce the influence of errors in the conductometric titration to a minimum, the angle between the two branches of the titrations should be as small as possible. If the angle is very obtuse, then a small error in the conductance data can cause a large deviation. So the main advantages of conductometric titration are its applicability to a very dilute and colored solutions, and to systems that involve relative incomplete reactions. For example, where neither a potentiometric or indicator method can be used, then a conductometric endpoint can be successfully applied. So acid base titration, especially at trace levels, then in that case conductometric titrations, they can be applied. The electrical conductance of a solution, it is a measure of its current carrying capacity, and therefore it is determined by the total ionic strength. It is a non-specific property, and for this reason direct conductance method are of little use, and they unless the solution contains one of the electrolyte. Conductometric titrations, in which the species is solution, they are converted to non-ionic form by neutralization, precipitation, and thereof they have more value. So some typical conductometric titrations, they had been discussed here. So this part we will study in the next class. This much for today, and here we'll start with conductometric titration curves in the next class. So this much for today.